The number Saul Perlmutter kept getting back was not supposed to be possible, and for 3 months he assumed the fault was his. This was Building 50B, Lawrence Berkeley National Laboratory, 1997. Not a glamorous address for the work being done inside it. Perlmutter was running the supernova cosmology project, and the project was pipeline work, systematic, methodical, designed to remove as much human judgment from the process as possible. You scheduled telescope time, you imaged a patch of sky, you came back 3 weeks later and imaged the same patch again. Software compared the 2 images and flagged anything that had changed. You confirmed the flagged objects, measured them, logged them, moved on. It was, by the standards of cosmology, almost clerical. But what the pipeline was measuring mattered enormously, because Type 1a supernovae are standard candles. They all explode at approximately the same intrinsic brightness. Measure how bright one looks from Earth and you can calculate how far away it is. Measure how fast it is moving away from you, the redshift in its light, the stretching of wavelengths as space carries the source away, and you can calculate how the universe's expansion has changed over the billions of years that light spent traveling toward your telescope. Accumulate enough of these measurements across enough distances, and you can map the expansion history of the universe. You can find out whether gravity is winning, pulling back on the Big Bang's initial outward push, slowing the expansion down, or losing. Everyone expected gravity to be winning. This was not a casual assumption. It was embedded in 60 years of cosmological modeling that had survived every encounter with data. The universe began expanding at the Big Bang. Gravity, acting on all the matter the universe contains, had been working against that expansion ever since. The question was only the rate of deceleration, how much gravity was winning by, because from that number you could calculate the universe's ultimate fate. Slow enough deceleration and the universe expands forever, thinning toward cold and darkness. Strong enough deceleration and expansion halts, reverses, and everything collapses back to a point. Both outcomes were understood, both had been modeled, and the data was going to tell you which one was real. What the data told Perlmutter's team was neither. The supernovae at high redshift, the ones whose light had been traveling toward Earth the longest, crossing billions of years of expanding space before arriving at the telescope, were dimmer than they should have been. Not dramatically dimmer. The dimming was subtle enough that in any individual measurement it could be explained by a dozen mundane causes. Dust in the line of sight, absorbing light before it reached the detector. A calibration error. A systematic bias in which supernovae the pipeline selected. Perlmutter's team worked through each possibility in sequence, because this is what you do when the number coming back is impossible. You look for the mistake. You rule out dust by checking the color signature. Dust affects blue and red wavelengths differently, and if dust is the culprit, the color tells you. They checked. It was not dust. They checked the instrument. They checked the software. They checked their selection criteria. Each check came back clean, and each clean check made the number harder to dismiss. The number, if it was real, meant only one thing. The supernovae were farther away than their redshift predicted. And if they were farther away than their redshift predicted, the expansion of the universe was not decelerating. It was accelerating. Something was pushing space apart, had been pushing it apart for billions of years before the solar system formed, before the Earth condensed from the debris around a young star, before any chemistry on any planet had assembled itself into anything capable of measuring light. The process this script was titled after did not begin in 1997. Perlmutter's measurement was simply the moment it became legible. Across the country, Brian Schmidt's High-Z supernova search team was getting the same number back. Schmidt was working out of the Harvard-Smithsonian Center for Astrophysics. His approach was collaborative, where Perlmutter's was systematized a distributed group of astronomers, sharing telescope time and data across institutions. Both teams knew the other existed. Both teams knew the other was working the same problem. There was no hostility exactly, but there was a specific quality of attention that comes from knowing that being second to publish a result of this magnitude means being remembered as second. Every measurement carried that weight. Adam Rees was 28 years old when the weight landed directly on him. He had just completed his PhD. His job on Schmidt's team was the data analysis, taking the raw supernova measurements and running the calculation that would produce the result. He was the one who actually processed the numbers that came back wrong. He later described his first response not as excitement, but as something he called dread. He named the anomalous data points the albino results, the ones that don't fit, the ones you run again because they have to be an error. They were not an error. Rees was 28, alone with a calculation showing the universe accelerating toward its own dissolution, and his first hours with that knowledge were spent looking for what he had done wrong, not because he was incurious, because the alternative, the possibility that the result was real, required the existence of something that appeared nowhere in established physics. Not in general relativity, not in the standard model of particle physics, not in any framework developed to describe how the universe actually behaves at fundamental scales. If the acceleration was real, something was causing it, and that something was, in the most literal sense, unknown. Both teams published in 1998. The results were consistent, the conclusion identical. The expansion of the universe is accelerating. The cause was given a name, dark energy, and that name has always been, from the day it was coined, a formal acknowledgement of ignorance. Dark energy is not an explanation. It is the label you put on a phenomenon when you can describe it precisely and understand it not at all. To understand what was actually found, you have to go back further than 1997. Much further. You have to go back to 1933, to a difficult man at the California Institute of Technology who found something the field spent 40 years refusing to believe. Fritz Zwicky was Swiss-American, brilliant, combative, and constitutionally incapable of softening a conclusion he believed the data supported. In 1933, he was studying the Coma Cluster, a dense collection of galaxies approximately 320 million light-years away. He measured the velocities of individual galaxies within the cluster and applied the virial theorem, a standard tool for calculating the total mass of a gravitationally bound system from the motions of its members. The answer came back wrong. The galaxies were moving far too fast. The visible mass of the cluster, all the stars and gas you could see, was nowhere near enough to gravitationally hold those velocities. The galaxies should have flown apart. They had not. Something was holding them, something invisible, present in enormous quantities, producing gravitational effects without producing any light. Zwicky called it dunkle materie, dark matter. He published. The field largely moved on without him. He described his colleagues in a phrase that became famous for reasons that had nothing to do with his cosmology, as spherical bastards in every direction you looked at them. They returned the assessment in the gentler language of institutional dismissal. His dark matter findings sat in the literature for 4 decades, cited occasionally, taken seriously almost never. He died in 1974. The year Vera Rubin's work began to make his finding undeniable. Rubin was at the Carnegie Institution of Washington, working with her collaborator Kent Ford. Ford had built an instrument, an image tube spectrograph, that was sensitive enough to measure the rotation velocities of stars and gas at the outer edges of galaxies. A galaxy rotation curve plots how fast stars orbit at different distances from the galactic center. Standard physics predicted that stars at the outer edges should orbit more slowly, the same way the outer planets of the solar system orbit the sun more slowly than the inner ones. The mass is concentrated at the center. The farther you are from the mass, the weaker its gravitational pull, the slower your orbit. Rubin and Ford pointed Ford's spectrograph at the Andromeda galaxy. They measured velocities at different distances from the center. The curve should have fallen high velocities near the center, declining as you moved outward. The curve was flat. Stars at the outer edges of Andromeda were orbiting at approximately the same velocity as stars close to the center. They were moving faster than the visible mass could account for. Something invisible was providing additional gravitational pull across the entire disk. and beyond it a halo of mass extending far beyond the visible galaxy, holding the outer stars in orbits they had no business maintaining given what the luminous matter alone could produce. Rubin and Ford published in 1970. Then they measured another galaxy. Then another. Then dozens. The flat rotation curve appeared everywhere they looked, in spirals, in ellipticals, in galaxies of different sizes and luminosities, and star formation histories. The result was not a peculiarity of one system. It was a universal feature of galaxies, and it meant that the visible universe, everything you can see with a telescope, everything that emits or reflects light, is a small fraction of the total mass that actually exists. Most of what is out there is dark. Zwicky had found this in clusters. Rubin and Ford found it in individual galaxies, systematically, without exception. In data so consistent that explaining it away required more effort than accepting it. The dark matter that Rubin and Ford spent a decade establishing is not a peripheral detail in the story of the universe's death. It is load-bearing. The cosmological model within which Perlmutter's team was working, the model that gave the measurement of accelerating expansion its meaning, treats dark matter as a known constituent of the universe. The total energy budget of the cosmos, as understood today, is approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. Remove dark matter from that accounting, and the framework that makes dark energy legible collapses. The 1997 discovery stands on the foundation Rubin and Ford built. Vera Rubin died in December 2016, at 88 years old. The Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees in 2011 for the discovery of the accelerating expansion. Rubin was nominated. She was discussed. The prize is not awarded posthumously. Zwicky died having been dismissed for 40 years. Rubin died having been passed over. The universe, indifferent to both, continued doing what it had been doing since before any of them were born. To understand why it was doing it, why the expansion was accelerating, what was pushing space apart, where this process had been heading before the Earth existed, you need the equation that a man in Vienna spent 20 years defending and died 2 years before it was proved correct. Ludwig Boltzmann was an Austrian physicist who, in the 1870s and 1880s, constructed what became statistical mechanics, the mathematical framework describing how the behavior of enormous numbers of tiny particles produces the large-scale properties we observe in matter. Temperature is not a property of individual atoms. It is a statistical property of enormous collections of them. Pressure is the cumulative effect of countless molecular collisions. The flow of heat from hot to cold is not a fundamental law imposed from outside, it emerges from probability. There are vastly more ways to arrange atoms in a disordered configuration than in an ordered one. Systems move toward disorder because disorder is more probable. That is the second law of thermodynamics, and it is the closest thing to a universal description of the direction of time that physics contains. Boltzmann's contribution was the equation that quantified this precisely. Entropy, the measure of disorder, the quantity that the second law says can only increase, is proportional to the logarithm of the number of microscopic arrangements that produce a given observable state. A state that can be produced by many different microscopic arrangements has high entropy. A state that can only be produced by a few arrangements has low entropy. High entropy states are overwhelmingly more probable than low entropy states, and systems move toward them spontaneously, because that is what probability means when applied to systems of trillions of particles. The reason a star burns rather than unburns is entropy. The reason a galaxy forms rather than unforms, the reason matter clumps rather than unclumps during the right conditions, the reason you age and do not unage, these are all the same phenomenon at different scales. The universe moves from ordered states toward disordered ones because disordered states are more probable, and more probable states are what you get when you wait long enough. Boltzmann's contemporaries spent 20 years trying to destroy this framework. Not because it was not wrong, but because it rested on the existence of atoms, and in the 1870s atoms were not established. They were a theoretical convenience. Ernst Mach, one of the most influential philosophers of science in Europe, argued that unobservable entities had no place in serious physics. If you cannot see it, it should not be in your equations. Boltzmann spent 2 decades defending the reality of atoms against an opposition that believed the defense was a category-error philosophy dressed as physics. He was right. They were wrong. Being right did not protect him from the sustained institutional dismissal that eroded his mental health across the same 2 decades. He died by suicide in 1906 in Duino, near Trieste. 2 years later, Jean Perrin's experiments on Brownian motion provided direct experimental confirmation of the atomic theory. The confirmation arrived after the man who needed it most was gone. What Boltzmann left behind was an equation carved on his tombstone in Vienna's Central Cemetery. S equals K times the log of W. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. It is, in a specific and non-metaphorical sense, the equation that describes why the universe is dying, because it defines what dying means. Now ask the question Boltzmann himself identified and could not fully answer. If the universe moves naturally toward high-entropy states, and high-entropy states are vastly more probable than low-entropy states, why did the universe begin in an extraordinarily low-entropy state? The Big Bang was not chaos. That is the common image, and it is wrong in a way that matters. The matter and energy of the early universe were distributed with a smoothness, a homogeneity that is, by Boltzmann's measure, almost unimaginably improbable. Every star that has ever burned, every galaxy that has ever formed, every living thing that has ever metabolized, every measurement Vera Rubin ever made, every calculation Adam Riess ran the night the number came back wrong, all of it. Is the universe moving from that initial low-entropy state toward the high-entropy state it is inevitably approaching? The dying did not begin with the discovery of dark energy. It began at the first second. Roger Penrose put a number on the improbability of that beginning. Working in 1979 through the implications of Boltzmann's entropy framework applied to the universe as a whole, Penrose calculated the probability of the specific low-entropy initial state the Big Bang began with. The number he arrived at required writing a 1 followed by 10 to the power of 10 to the power of 123 zeros. There is no analogy that preserves the scale of this. The total number of atoms in the observable universe is approximately 10 to the 80. Penrose's number for the improbability of the initial state dwarfs that by a margin so absolute that the comparison is almost meaningless. The universe should, by every statistical argument available, have begun in a high-entropy state. It did not. It began in a state of almost perfect order, and everything since has been the repayment of that initial improbability. The question Penrose's number raises without answering is why. The most prominent proposal is cosmic inflation, the idea that in the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, stretching any initial irregularities smooth and producing the homogeneous starting condition we observe. The cosmic microwave background radiation, the thermal afterglow of the Big Bang that permeates the entire sky at a temperature of 2.7 Kelvin, supports this. Its uniformity, the fact that regions of sky that have never been in causal contact with each other have almost exactly the same temperature, is most naturally explained by inflation having stretched them from a common region before they separated. But inflation does not close the question. It requires its own low-entropy initial condition. The inflated field that drove the rapid expansion had to be configured in a specific way to produce the inflation we observe. Push the question back before inflation and it survives. Somewhere, at the very beginning, the universe was given an improbably ordered state. The dying that Perlmutter's pipeline detected in 1997 is the process that Gift set in motion, arriving finally at a measurement after billions of years of being too large and too slow to read from inside. Albert Einstein encountered the edge of this in 1917, before inflation was a concept. before the expansion of the universe was known, before anyone had the instruments to look far enough to see what was happening. He had completed his field equations for general relativity in November 1915. The equations described how matter and energy curve space-time, and how that curvature governs the motion of everything within it. When he applied them to the universe as a whole, they gave him a problem. The mathematics would not permit a static universe. The equations predicted a universe in motion expanding or contracting, never simply sitting still. And in 1917, a universe in motion was not a concept that existed. The idea that the cosmos had a beginning, that it was evolving from one state toward another, that it had a direction, none of this was available. So Einstein added a term to his equations. He called it the cosmological constant. Lambda, a repulsive energy density built into the fabric of space itself, calibrated precisely to balance gravity and hold the universe static. The equations, with lambda included, permitted a universe at rest. The problem went away. 12 years later, Edwin Hubble published observations showing that every distant galaxy was moving away from every other, the whole universe spreading outward, the farther galaxies receding faster, the pattern unmistakable. Einstein, on learning this, described the cosmological constant as the greatest blunder of his career. He removed it. Lambda became a warning in the history of physics, the canonical example of a fudge factor introduced to preserve a belief the data was about to destroy. What Perlmutter and Rias found in 1997 was that the blunder was not a blunder. The cosmological constant, or something that behaves exactly as it would, is real. It is present. It is doing precisely what Einstein's mathematics said something with its value would do, pushing space apart, working against gravity at cosmic scales, accelerating the expansion. Einstein introduced it for the wrong reason, removed it for the wrong reason, and it turned out to be correct for reasons that remain, as of the current date, entirely unknown. The measured value of the cosmological constant is approximately 1.1 times 10 to the negative 52 per square meter. That number is the most embarrassing figure in theoretical physics. Not because it is wrong, because it is right. And quantum field theory, the most precisely confirmed theory in the history of science, in every other context it has been applied, predicts a value 120 orders of magnitude larger. 120 orders of magnitude. The total number of atoms in the observable universe is 10 to the 80. The discrepancy between the predicted and observed cosmological constant is 10 to the 120. The theory does not miss by a little. It misses by a factor that defeats any ordinary description of wrongness. If quantum field theory's prediction were correct, the vacuum energy of space would be so enormous that the universe would have been torn apart in the first instant after the Big Bang. There would be no galaxies, no stars, no atoms, no time for any process to occur. The universe would have expanded so violently and immediately that no structure of any kind could have formed, including the physicists doing the calculation. Instead, the value is almost exactly zero. Something cancels almost all of the vacuum energy. Not all of it, the residue, is real and measurable. And it is the residue that is driving the acceleration. No one knows what performs the cancellation. No one knows why the residue is the specific value it is, rather than some other value equally close to zero. This is called the cosmological constant problem, and it has been called the worst prediction in the history of science for more than 25 years without resolution. This is not background to the story. This is the story. The universe is dying. Yes, the expansion is accelerating. Yes, dark energy is real. Yes. And underneath all of it, the force driving the dying is a value we can measure and cannot explain. Predicted by our best theory to be a number that would have made existence impossible, actually being a number so close to zero that life was possible, but not so close that the dying stopped. To understand what the dying looks like, what the universe is actually approaching, what the process that started before Earth existed is moving toward, you have to leave 1997 and travel forward. Not to darkness and silence, not to the borrowed imagery of extinction, but to a sequence of specific events with specific mechanisms and specific timescales, each stranger than the last. Star formation is already in decline. The Milky Way currently forms approximately 3 solar masses of new stars per year, down from a peak roughly 10 times that rate around 10 billion years ago. Stars require hydrogen, and the galaxy's hydrogen supply is finite. It is being consumed. The rate of consumption is slowing as the available fuel diminishes, but the direction is fixed. Approximately 100 trillion years from now, the last star will exhaust its fuel and go dark. 100 trillion years is roughly 7,000 times the current age of the universe. We are, by any cosmic accounting, still in the early afternoon of the era of stars. But the era of stars has a closing time, and the reservation was made at the beginning. After the last star dies, the universe is left with what stellar evolution produces: white dwarfs, neutron stars, black holes. White dwarfs are the dense, hot cores of exhausted stars, supported against gravity not by fusion, but by the quantum mechanical resistance of tightly packed electrons. They cool slowly, radiating their stored heat into the expanding dark over timescales of trillions of years. In the era after stars, white dwarfs will be among the last warm things anywhere, fading embers of the stelliferous age, cooling toward the ambient temperature of a cosmos that grows colder and emptier every year. Whether they last indefinitely depends on a question that decades of experiment have not resolved. The proton may be unstable. Certain extensions of the standard model of particle physics theories attempting to unify the strong and weak nuclear forces and electromagnetism into a single framework predict that protons decay, with lifetimes of at least 10 to the 34 years. The Super Kamiokande detector in Japan, a tank containing 50,000 tons of ultra-pure water surrounded by photomultiplier tubes, sensitive enough to detect the light produced by a single high-energy particle, has been watching for the signature of proton decay since 1996. It has not found one. Each year of null results pushes the lower bound on the proton lifetime higher and rules out additional theoretical models. The proton, if it decays, lives longer than any experiment has yet been able to confirm. But the experiments have not proven stability. They have only established a floor. If protons decay, white dwarfs dissolve slowly, the nuclear material within them disintegrating into lighter particles, releasing faint energy as they go. The last warmth of the stelliferous era would come not from fusion, but from the quiet quantum disintegration of the matter that stars spent their lives forging. The black holes remain regardless. They are the most durable objects the universe produces, and for a very long time after everything else has gone quiet, they dominate. The supermassive black hole at the center of the Milky Way Sagittarius A star, 4 million solar masses, will grow as stellar remnants sink toward it over billions of years. Smaller black holes throughout the galaxy and beyond will persist in the cold. Gravitational interactions between the remaining objects will, over timescales of 10 to the 19 to 10 to the 20 years, eject most of the white dwarfs and neutron stars from the galaxy, entirely flung out into intergalactic space in the slow gravitational dance of close approaches, while the survivors spiral inward toward the central mass. And then Stephen Hawking's 1974 calculation arrives, and the character of the dying changes entirely. Hawking showed that black holes are not perfectly black. Working at the intersection of quantum mechanics and general relativity, he demonstrated that the vacuum at the edge of a black hole's event horizon is not truly empty. Quantum fluctuations produce pairs of particles, one falling in and one escaping, with the escaping particle carrying energy away from the hole. The energy comes from the black hole's mass. The hole is losing mass as it radiates. The process is called Hawking radiation, and for any black hole in the current universe it is extraordinarily faint. The Hawking temperature of a stellar mass black hole is approximately 100 nanokelvins, compared to the current cosmic microwave background temperature of 2.7 Kelvin. The ambient radiation bath is warmer than the black hole's emission, so the hole absorbs more than it radiates and grows. But as the universe expands and the CMB temperature falls, A time comes when the ambient temperature drops below the Hawking temperature, and from that point the black hole loses mass faster than it gains it. The evaporation is slow in ways that challenge description. A stellar mass black hole evaporates completely in approximately 2 times 10 to the 67 years. A supermassive black hole billions of solar masses takes somewhere between 10 to the 90 and 10 to the 100 years. Against these timescales, the current age of the universe is not even a rounding error. But the evaporation is not indefinite. It ends, and it does not end quietly. As a black hole loses mass, its Hawking temperature rises. Temperature is inversely proportional to mass in this context. The smaller the hole gets, the hotter it radiates, the faster it loses mass, which makes it smaller still, which raises the temperature further. The final stages of a black hole's evaporation are not a slow fading. They accelerate. The last fraction of the hole's mass converts to energy in a burst of high-energy radiation. The black hole does not go quiet at the end. It goes off. After that final burst, after the last supermassive black hole has fired its terminal signal into a cosmos with nothing left to receive it, what remains? Photons from every Hawking burst ever emitted, spreading outward through an expanding space. Electrons and positrons at densities so low they will almost never encounter each other. Neutrinos, gravitational waves from mergers that happened so long ago, the concept of long ago has lost its meaning. And the dark energy, the cosmological constant, the thing that has no explanation, still present, still doing what it has always done, pushing space apart. The universe is now in what cosmologists call the dark era. No stars, no black holes, an expanding, cooling expanse in which the remaining particles are separated by distances that make the current observable universe feel intimate. And it is still accelerating. The dark energy that Perlmutter's team spent 3 months trying to explain away continues working, and there is nothing left for it to work against. The endpoint this process is approaching has a specific temperature, not zero. The cosmological constant, if it is truly constant, implies a minimum temperature that the universe approaches, but cannot reach the Gibbons-Hawking temperature, approximately 2.3 times 10 to the negative 30 Kelvin. A number so small the difference between it and zero is unmeasurable by any instrument that could exist, but it is not zero. The dark energy filling space generates a thermal radiation analogous to Hawking radiation, a quantum mechanical consequence of the cosmic event horizon that the accelerating expansion creates, and that radiation means the universe will always have a temperature, always be technically, precisely, distinguishably above absolute zero. Not for a long time. Forever, this is the heat death. Not darkness and silence. A universe humming at 2.3 times 10 to the negative 30 Kelvin, expanding without end, with nothing in it capable of interacting with anything else, carrying the history of every star and galaxy and black hole as photons too diffuse to ever find a receiver. Not dead. Dying. The process that began at the Big Bang, in the improbably ordered initial state that Penrose put a number on, never reaches its conclusion. Entropy approaches maximum as a limit. Maximum entropy, the final equilibrium where no work can be extracted, no temperature differences remain, no process can be driven, is the attractor the universe has been falling toward since the first second. It approaches it forever. It does not arrive. But the heat death assumes the cosmological constant is constant, that dark energy maintains its current character indefinitely. This is the assumption the data currently supports, but there is a meaningful difference between constant and not yet changed enough to notice. Robert Caldwell, a physicist at Dartmouth College, published a paper in 2002 that named the alternative and worked through its implications with a precision that was, by his own account, disturbing to carry to completion. In models where dark energy is not a fixed property of the vacuum, but a field with dynamics, what theorists call phantom energy, its effective pressure can grow stronger over time. In Caldwell's calculation, if dark energy has the right character, the acceleration does not merely continue, it increases. The force pushing space apart grows stronger every year, and it grows without limit. Caldwell's paper traced what this means, step by step. At first, only the largest structures feel it, galaxy clusters being pulled apart as dark energy's push overwhelms gravity across their hundreds of millions of light years of extent. Then individual galaxies. Gravity holds the Milky Way together against the current expansion, but a growing dark energy eventually overwhelms that too. Then solar systems. Then the gravitational bond between the Earth and the Sun. Then the electromagnetic force holding matter together, the force that makes solid objects solid, that keeps atoms in molecules, that holds the molecules of your body in the configuration that constitutes you. That force, too, is overwhelmed. In the final moments of Caldwell's calculation, atomic nuclei are torn apart by the expanding space between their constituent protons and neutrons. Then the protons and neutrons themselves. Then, at the last instant, space tears, the expansion becomes infinite in finite time, producing a singularity not at the beginning of the universe, but at its end. Caldwell called it the Big Rip. It is not darkness and dissipation. It is everything that exists, at every scale simultaneously, pulled apart by the same force that currently appears in Perlmutter's data as a slight dimming of distant supernovae. The Big Rip requires dark energy to have a specific equation of state, a ratio of pressure to energy density below -1, what physicists call the phantom regime. Current measurements are consistent with exactly -1, a true cosmological constant, but the uncertainties are large enough to include phantom values. The difference between a quiet heat death and the total structural dissolution of everything is, with current instruments, within the noise. This is not a comfortable position for cosmology to occupy. The character of the universe's ending is undetermined by current observation. Meanwhile, in the almost unimaginably long interval between now and either ending, something that Boltzmann noticed keeps accumulating significance. If the universe exists in a state of near maximum entropy for long enough, and long enough here means timescales that make 10 to the 100 years look like a moment, random statistical fluctuations will occasionally produce regions of lower entropy. This is not speculation, it is probability. In a system at near equilibrium with infinite time available, fluctuations of every size will eventually occur, with probability decreasing exponentially with the size of the fluctuation. Given enough time, a fluctuation large enough to spontaneously assemble a single self-aware observer, a brain essentially, that emerges from thermal noise with apparent memories and perceptions intact, will occur. These are called Boltzmann brains, and they are one of the more genuinely destabilizing ideas in cosmology, not because they are exotic, but because of what they imply. The problem is this: if the universe spends an infinite future in near equilibrium, which the accelerating expansion with a permanent cosmological constant appears to guarantee, the total number of Boltzmann brains produced by thermal fluctuations over that infinite future may vastly outnumber the total number of structured, evolved, embodied observers produced during the entire stelliferous era. Every observer who has ever existed across the full span of cosmic history during which stars burned and complexity was possible may be outnumbered by the brains that fluctuate into existence in the long quiet afterward. And if most observers in the universe's history are Boltzmann brains, instantaneous fluctuations with false memories rather than real histories, then the probability that any given observer is a Boltzmann brain rather than a real one is very high. This is not a philosophical puzzle at a comfortable remove. It is a coherence problem embedded in the theory itself. A cosmological model that predicts a permanent cosmological constant and an infinite future of near equilibrium generates, as a consequence of that prediction, the conclusion that most observers have unreliable perceptions, which means the observations used to confirm the permanent cosmological constant cannot be trusted, which means the model cannot confirm itself. The theory, pushed to its ultimate implications, undermines the observers who constructed it. Most cosmologists set this aside as a problem for the far future. But problems set aside do not go away. They wait. All of this, the Boltzmann brains, the evaporating black holes, The heat death, the cosmological constant problem that makes the whole edifice rest on a number no one can explain, hangs on the work of people who paid for it in ways the institutions of science did not fully account for. Zwicky found dark matter in 1933. He spent the remaining 4 decades of his life watching the field move around his finding without crediting it. His combativeness was real, and it gave the field a convenient reason to keep its distance. But the convenience of the reason does not make the dismissal accurate. He was right about dark matter. He was right about neutron stars before neutron stars were confirmed. He was right that galaxies could act as gravitational lenses for the light of more distant objects, a technique that is now among the most powerful in cosmology decades before anyone demonstrated it. Being right is not the same as being heard, and the gap between those two things is where Zwicky spent most of his career. Rubin's gap was different in character but identical in structure. The flat rotation curves were not ambiguous data. They were consistent, systematic, reproduced across dozens of galaxies, and explicable by dark matter in a way that required no exotic new physics beyond its existence. The field eventually accepted this. It accepted it while Rubin was alive. Watching the Nobel discussions happened while she was alive. The prize went elsewhere. She received the National Medal of Science in 1993 and the Gold Medal of the Royal Astronomical Society in 2004, and she received neither as a consolation. She had earned both independently of the Nobel question. But the Nobel question was real, and the answer the committee gave, year after year until 2016, was silence. The people who found the evidence that the universe is dying paid for the finding. Boltzmann paid with 20 years of institutional dismissal and his life. Zwicky paid with a career spent in the margins of a field he had outrun. Rubin paid with the specific recognition she did not receive for the work that made dark energy comprehensible. Ries paid at 28 with dread, with the experience of sitting alone with a number that should have felt like triumph, and felt instead like the floor had gone. The universe paid nothing. The universe does not pay. That is what indifference means when the word is used with precision rather than metaphor. The dark energy did not slow, while Rubin's nomination was considered. The entropy did not pause for Boltzmann's confirmation to arrive 2 years earlier. The acceleration Perlmutter measured had been proceeding for billions of years before anyone was in a position to measure it, and it will proceed for billions of years after the instruments used to measure it have dissolved along with everything else. The dying started before Earth existed, because the dying started at the beginning. The Earth condensed from the debris disk around a young sun approximately 4.5 billion years ago. The solar system formed from a cloud of gas and dust that itself coalesced from the materials scattered by previous stellar generations. Those earlier stars burned and died in supernovae that seeded the interstellar medium with the heavy elements carbon, oxygen, iron. Everything heavier than helium that eventually became the Earth, the biosphere, the chemistry of living things, the neurons firing in the brain of every person who has ever looked at the night sky and wondered what they were looking at. The universe was already 9 billion years old when the Earth formed. The cosmological constant had been accelerating the expansion for most of that 9 billion years. The entropy of the universe had been increasing since the first second. Every star that burned during those 9 billion years was the universe consuming its initial gift of order, converting the low-entropy structured fuel of hydrogen into the higher entropy disordered output of light and heat. The Earth formed into a universe already well into its dying, surrounded by stars that were themselves expressions of the dying, sustained by a sun that is burning through its fuel on a timeline that will end in approximately 5 billion years. You are made of material from stars that completed their dying before the Earth existed. The carbon in your cells, the oxygen in your blood, the calcium in your bones, these were forged in stellar interiors and released into space when those stars ended, and they drifted in molecular clouds for millions of years before gravity assembled them into the solar nebula, and the solar nebula collapsed into the sun and its planet. And billions of years of chemistry and evolution produced the configuration of matter currently reading these words. You are stellar ash. You are a temporary structure assembled by the dying universe from the wreckage of earlier structures. and you are yourself an entropy-increasing process. Metabolism consumes ordered fuel and releases heat and disorder. Thinking is thermodynamically expensive. Existing is thermodynamically expensive. Every moment of your life increases the entropy of the universe by a small but real amount. You are not separate from the dying. You are made of it. This is not a poetic reframing of a scientific fact. It is the scientific fact, stated without the softening that usually surrounds it. The complexity of life, the emergence of metabolism, of reproduction, of consciousness happens in a specific region of the entropy spectrum. Too ordered and no processes can occur. Too disordered and no structures can persist. Life emerges in the middle territory, where entropy is high enough for complex chemistry but not so high that everything has already equilibrated. The universe is currently in that middle territory. It will not stay there. The middle territory is a transit zone, not a destination, and the transit has been in progress since the first second. What Perlmutter found in Building 50B is that the transit is accelerating. The universe is moving through the middle territory faster than gravity alone would have allowed, pushed by the cosmological constant toward the diffuse, cold, isolated endpoint where the middle territory ends and the eternal near equilibrium begins. Every galaxy receding beyond the cosmic event horizon is a region of the middle territory the universe has lost permanently, irreversibly. The information it contains sealed away from every other region by the expanding space between them. The isolation is not a future threat. It is a present condition. Right now, as of this moment, light emitted from galaxies beyond a certain distance will never reach the Milky Way. The universe has already begun the fragmentation that the heat death completes. The cosmic microwave background, the 2.7 Kelvin thermal afterglow that Rubin's observations were made against, the radiation field that the first measurements of the accelerating expansion had to account for, is itself a relic of the dying. It is the cooled remnant of the radiation that filled the early universe when it was opaque, when matter and energy were in thermal equilibrium and photons could not travel freely. As the universe expanded and cooled, the plasma of the early universe recombined into neutral hydrogen. The universe became transparent, and the photons that had been trapped in the plasma were released. They have been traveling freely ever since, cooling as the universe expands, shifting from the high-energy radiation of the hot early universe toward the microwave frequencies we now detect. The CMB is not a signal from the beginning. It is a record of the cooling, the photographic negative of the moment the universe first became transparent to its own light, pressed into the microwave sky by 13.8 billion years of expansion. It will keep cooling. As the universe expands, the CMB temperature will continue to fall. The photons will redshift toward longer and longer wavelengths. Eventually, they will be indistinguishable from the Gibbons-Hawking radiation that the cosmological constant generates, the irreducible thermal minimum of an accelerating universe. At that point, what remains of the CMB will be absorbed into the background hum of the dark energy itself, and the last observable relic of the Big Bang will be gone. What persists in the dark era is a question about information. When a black hole evaporates, what happens to the information about everything it ever consumed? The matter that fell in the stars, the gas, the light, the information encoded in every particle's state, does it survive in some form in the Hawking radiation, or is it destroyed? This is the black hole information paradox, and it has been among the central unresolved problems in theoretical physics since Hawking himself identified it in the 1970s. If information is destroyed, quantum mechanics is violated. The theory requires that the evolution of quantum states be reversible in principle, and the destruction of information would break that. If information is preserved in the Hawking radiation, the mechanism of preservation is unknown, and the implications for the structure of spacetime at the event horizon are radical. The paradox matters for the dying because if information is destroyed in black hole evaporation, then the universe's final state after all black holes have evaporated is a state from which nothing of the past can in principle be recovered. Not merely inaccessible. Gone, the history of the universe, encoded in the states of its particles across 13.8 billion years of structure and complexity, would be irretrievably lost. The dying would be not just thermodynamic, but informational, not just the dissolution of order, but the erasure of the record that order ever existed. Most physicists, following arguments developed by Juan Maldacena and others in the framework of the ADS-CF correspondence, now believe information is preserved, that Hawking radiation carries the information encoded in the infalling matter, scrambled beyond any practical recovery, but in principle present. Hawking himself accepted this position late in his career, conceding a bet he had made with Kip Thorne and John Preskill in 1997, the same year Perlmutter and Ries were finding their impossible numbers. But the mechanism of preservation, the precise account of how the information escapes in the radiation, remains unsettled. The resolution that most physicists accept is a conclusion in search of a mechanism. This matters because the mechanism is the physics. Knowing that information is probably preserved is not the same as knowing how, and how is where the actual understanding lives. The dying universe carries within it, in its evaporating black holes, one of the deepest unresolved questions in physics, not because the question is abstract, but because the answer will determine whether the universe's history, in any sense, survives its own ending. Ries was 28 when he sat with the number that filled him with dread. He went on to win the Nobel Prize 13 years later, to hold the Bloomberg Distinguished Professorship at Johns Hopkins, to continue the work of measuring the universe's expansion with increasing precision. The dread, he has said in interviews, did not leave with the confirmation. The measurement that made him famous is a measurement of the universe accelerating toward a state that no theory adequately explains, driven by a force that carries a name and nothing else. The Hubble tension complicates even this. In the years since 1998, two independent methods of measuring the expansion rate of the universe, what cosmologists call the Hubble constant, the rate at which the universe is currently expanding, have produced results that disagree. Measurements based on the early universe using the CMB give a Hubble constant of approximately 67.4 kilometers per second per megaparsec. Measurements based on the local universe, using the distance ladder of standard candles including Cepheid variable stars and Type 1a supernovae, the method Perlmutter and Ries developed, give a value closer to 73 kilometers per second per megaparsec. The discrepancy is small in absolute terms. In statistical terms, it has now exceeded 5 sigma, the threshold at which physicists consider a result not merely suggestive, but a genuine signal. A real difference that requires a real explanation. No explanation has been confirmed. Systematic errors in one or both measurement methods remain possible and have been investigated extensively. New physics, something in the early universe that the standard cosmological model does not account for, is another possibility. The Hubble tension may be the first hint of a crack in the cosmological model that the 1997 discovery helped establish. Or it may be a systematic error that a better measurement will resolve. The data does not yet say which. What it says is that the universe is expanding, that the expansion is accelerating, that the cause is measured and unnamed, that the measurement is in tension with itself across two independent methods, that the initial conditions that set the dying in motion were so improbably ordered, that the probability of them arising by chance requires a number that exceeds the descriptive capacity of ordinary language, that the force driving the acceleration is predicted by the best available theory to be 120 orders of magnitude larger than it is, and that the people who established these facts paid for the establishing in ways that range from 2 years of fatal mistiming to a career in the margins to a Nobel nomination that arrived too late. Boltzmann's equation is on his tombstone, because his students chose it as the thing he had given the world that most deserved to outlast him. The people who chiseled it into the stone were putting the measure of disorder into the rock above a man who had been destroyed by the disorder of institutional recognition, the randomness of which truths get believed when, and by whom, and at what cost to the person who first found them. The universe does not organize its accounting around the timelines of the people inside it. This is not cruelty. Cruelty requires awareness of the thing it is being cruel to. The universe has no awareness of Vera Rubin, of Fritz Zwicky, of Ludwig Boltzmann, of the 28-year-old sitting in 1997 with a number he desperately wanted to be wrong. The entropy increases on the schedule set by the initial conditions and the cosmological constant, and the quantum mechanical properties of the vacuum. And the people who measure the increasing are expressions of the increasing, temporary structures assembled by the same process they are trying to understand, using the entropy gradient that is consuming everything to power the very awareness that notices it. This is the thing that changes the shape of everything above it. The universe is dying, and the dying is not happening to us. We are the dying. The complexity that produces consciousness, the ordered chemistry of cells, the neural structures that support awareness, the telescopes and pipelines and spectrographs and ultra-pure water tanks that generate the evidence, these are all expressions of the entropy increase. Temporary configurations of matter that the universe passes through on its way from the improbably ordered beginning toward the diffuse asymptotic end. We are not watching the universe die from outside. There is no outside. We are inside. We are made of it. And the awareness we have of the process is itself one of the things the process produces as it proceeds. The middle territory, the region between perfect order and perfect disorder where complexity is possible, is not permanent. The stars burning tonight are burning through the fuel that sustains the conditions for complexity. The universe is not maintaining the middle territory, it is moving through it. The transit began at the Big Bang, when the initial gift of order started dissolving. It accelerated, apparently, sometime in the last few billion years when dark energy, whatever it is, at whatever value our best theory cannot explain, overcame the gravitational deceleration that had been partially slowing the transit. And it will continue, the middle territory thinning, and the isolated regions growing, and the temperature falling toward, but never reaching the Gibbons-Hawking minimum, until the last black hole fires its terminal burst, and the last photons spread outward into a space so large and so empty that the word spread has lost its meaning. What began before Earth existed will continue after everything that Earth produced has dissolved. The atoms in your body were in stars before they were in you. And after you, they will be in something else, scattered back into the interstellar medium if you are cremated, incorporated into the soil and then into organisms, and then scattered further, cycling through the biosphere until the biosphere ends, and the Earth is consumed by the expanding sun, and the elements disperse into the solar wind and eventually into the thin interstellar medium of whatever the Milky Way and Andromeda have become. Those atoms will then cool for trillions of years in the darkness after the last star, and if protons are stable, they will persist in that darkness for timescales that make all of human history a rounding error, until the gravitational interactions of the dead galaxy scatter them into intergalactic space where they will drift, cooling. As the universe expands around them, separated from every other particle by distances that grow without limit. That is where the atoms in your body are going. Not metaphorically. Actually, the dying that Perlmutter spent 3 months trying to find his mistake in is the dying that will carry the specific matter of every specific person who has ever existed into the dark era and beyond. The number he kept getting back was not a mistake. It was the universe, after nearly 14 billion years of doing what it was always going to do, producing in one specific building at one specific institution a measurement legible to the people inside it. A number that said, the process started long before you were here. It will continue long after you are gone. And the rate at which it proceeds has been increasing, driven by something we do not understand, toward an end that approaches but never arrives. That is what Ries felt as dread at 28, not the number itself. What the number implied about everything, the duration of the process, the indifference of its mechanism, the smallness of the window in which anything as complex as a person can exist to notice it. The dread was accurate. It was the appropriate response to a finding that was accurate. The universe is dying for a reason, and the reason is that it began. And the beginning was so improbably ordered Penrose's number, the one that defeats comparison, that the correction has been underway ever since. And the correction is everything. Every star that has ever burned, every galaxy that has ever formed, every rotation curve Vera Rubin measured, every night Fritz Zwicky spent at the Palomar telescope finding things the field was not ready to believe, every year Boltzmann defended atoms against people who were wrong, every check Perlmutter ran looking for dust, looking for instrument error, looking for the mistake that would let him report something the universe was prepared to permit. The correction is everything, including this. The Hubble tension has a face, and it is not the face of a theory in comfortable disagreement with itself. Wendy Friedman has been measuring the expansion rate of the universe for longer than most of the people currently debating the Hubble tension have been in the field. She led the Hubble Space Telescope Key project in the 1990s, the effort to use the newly repaired space telescope to nail down the Hubble constant using Cepheid variable stars as distance markers. Cepheid variables pulse. They brighten and dim on a regular period, and the period is directly related to their intrinsic luminosity. A longer period means a more luminous star. Measure the period, calculate the true brightness, compare it to the apparent brightness as seen from Earth, and you have the distance. It is the same logic as Type 1a supernovae, applied to a different class of objects, and it had been the foundation of cosmic distance measurement since Henrietta Swan Leavitt established the period luminosity relationship in 1908 at the Harvard College Observatory. In a role the institution classified as computer, a person who performed calculations, not a scientist who made discoveries. Leavitt was not allowed to operate the telescopes she was analyzing the data from. She died of cancer in 1921, before Edwin Hubble used her period luminosity relationship to establish that the Andromeda Nebula was a separate galaxy and that the universe was expanding. She was nominated for the Nobel Prize after her death. The committee was informed she had died. The nomination lapsed. Friedman's Key project published its final result in 2001, a Hubble constant of 72 kilometers per second per megaparsec, with an uncertainty of about 10%. It was the most precise measurement of the expansion rate yet made, and it was understood as a foundation for the cosmological work that followed. When Perlmutter and Rees published their accelerating expansion results, those results were interpreted within a framework that assumed a Hubble constant in approximately this range. 2 decades later, Friedman measured it again, using a different class of standard candle, the tip of the red giant branch, a point in stellar evolution where stars of a certain mass undergo a brief, brilliant flare before settling into a new phase. The method is independent of Cepheids. It probes different systematic errors. Her 2019 result came in at 69.8 kilometers per second per megaparsec, closer to the early universe value from the CMB than to the local universe value from Cepheids and supernovae. The field, which had been organizing itself around a tension between roughly 67 and roughly 73, suddenly had a third data point sitting in between. This did not resolve the tension, it complicated it. If Friedman's tip of the red giant branch measurement is right, the Cepheid-based distance ladder has a systematic error, somewhere a bias in how Cepheids are calibrated, or how their distances are used to anchor supernova measurements. If the Cepheid measurements are right, Friedman's method has its own systematic, and if both are right, the tension is real. And the standard cosmological model, the model that treats the cosmological constant as the sole driver of the acceleration, that predicts a specific expansion rate as a consequence of its parameters, is missing something. The James Webb Space Telescope, which began science operations in 2022, was expected to resolve this. It has not resolved it. Webb's observations of Cepheids in the same galaxies that ground-based and Hubble observations had measured confirmed the Cepheid distances rather than overturning them. The Hubble tension survived the most powerful telescope ever built being aimed directly at it. As of current measurements, the tension persists. The explanation remains unknown. And a tension in the Hubble constant is not a small thing. Because the Hubble constant is the single number that sets the scale of the universe, the rate of everything, the conversion factor between distance and recession velocity, the parameter that anchors every cosmological measurement to every other. If the tension is real physics rather than systematic error, the implications extend well beyond the expansion rate itself. A Hubble constant higher than the CMB predicts could mean the universe is older than the CMB measurement suggests or younger. It could mean the early universe contained some component in additional relativistic particle species, or a brief episode of early dark energy that is not in the standard model. It could mean dark energy is not constant after all, that it evolved differently in the early universe than it does today. Each of these possibilities changes the shape of the dying. A universe with early dark energy has a different expansion history than a universe with only the cosmological constant. Different expansion history means different timeline for the stelliferous era ending, different conditions for the black hole era, different approach to the heat death. The dying the script has been describing the specific sequence of events. The specific timescales is derived from the standard cosmological model. If the Hubble tension points to new physics, those timescales may be wrong. Not wrong in direction, the direction is fixed by thermodynamics. And thermodynamics does not negotiate, but wrong in scale. The universe might be dying faster or slower than current models predict, driven by a dark energy that is not constant, toward an endpoint that differs from the heat death in ways current data cannot yet specify. This is not a comfortable position for cosmology to occupy. It has been in this position before. In 1998, when Perlmutter and Rees published the cosmological model that their results overturned had been considered well established. The deceleration of the expansion was expected. The confirmation of deceleration was the goal. The discovery that confirmed the opposite was not predicted by the model that framing the measurement. It came from inside the measurement itself, from data that kept coming back wrong. The field had been wrong about the sign of the acceleration. The Hubble tension raises the possibility that the field is wrong again, this time not about direction, but about the driver. Not about whether dark energy exists, but about what it is. Wendy Friedman has said publicly that she is not convinced the tension reflects new physics. She thinks systematic errors in the distance ladder are the most likely explanation, and she has spent years trying to find them. She has not found them. The tension has widened as the measurements have improved. Better instruments producing higher precision results in both the early universe and late universe measurements have not converged. They have, if anything, pulled further apart. The person who would know best is Henrietta Swan Leavitt, whose period luminosity relationship is the foundation of the local distance ladder. She is not available for comment. She died in 1921, before the tool she built was fully understood, working in a role that did not acknowledge her as a scientist, and the prize that might have come was stopped by her death. The dying of the universe is being measured with a ruler she made in a room where she was not considered capable of directing the instruments. That detail is not decorative. It is load-bearing in the same way Rubin's rotation curves are load-bearing. The infrastructure of cosmological knowledge, the observational framework within which questions about the universe's death can even be asked, was built partly by people whose contributions were structurally undervalued during their lifetimes and incompletely credited afterward. This is not a critique imposed on the history from outside. It is what the history contains when you look at it without deciding in advance what the story is about. Cecilia Payne-Gaposchkin determined in 1925 that stars are composed primarily of hydrogen and helium, that the Sun is not made of the same mix of elements as the Earth, as had been assumed, but is overwhelmingly hydrogen. Her PhD thesis at Radcliffe College contained this finding. Her thesis advisor, Henry Norris Russell, told her the conclusion was clearly wrong and persuaded her to add a disclaimer. 4 years later, Russell reached the same conclusion independently, published it, and received credit for it. Payne-Gaposchkin's thesis was later described by the astronomer Otto Struve as the most brilliant PhD thesis ever written in astronomy. The hydrogen composition of stars is the reason stellar evolution takes the form it does, the reason the stelliferous era has the timescale it has. the reason the dying proceeds on the schedule Penrose's calculations describe. Without knowing that stars are mostly hydrogen, the physics of how they burn, how long they burn, and what they leave behind cannot be correctly understood. The dying of the universe was being measured by people whose understanding of what they were measuring rested on a foundation built by someone whose name was not on the result. This is the pattern. It appears too consistently to be coincidence, and too structurally embedded to be simply the failure of individual committees. Leavitt's period luminosity relation, Payne-Gaposchkin's stellar composition, Zwicky's dark matter, Rubin's rotation curves. Each one is foundational. Each one came from someone whose institutional position made the foundational contribution harder to recognize in real time. The Nobel Committee operates on specific rules living recipients only, maximum of 3 per prize, and those rules were not designed to produce this outcome. But the outcome is what the rules produced, in combination with a field that moved slowly on some recognitions and quickly on others, for reasons that were not always purely scientific. None of this changes the physics. The entropy increases regardless. The cosmological constant drives the acceleration regardless. The heat death approaches regardless. The universe does not organize its dying around questions of attribution, but the people inside the dying, the people doing the measuring, building the instruments, running the calculations, sitting with the numbers that fill them with dread, exist inside institutions and histories that do organize themselves around questions of attribution, and those organizations have consequences that reach forward in time. A finding dismissed for 40 years is a finding that does not anchor subsequent work for 40 years. A contribution uncredited is a model incomplete. The cost is not only personal, it is epistemic. The field knows less, sooner, than it would have if the infrastructure of recognition had been more accurately calibrated to the infrastructure of discovery. Gravity wave astronomy arrived in 2015, when the LIGO detectors in Livingston, Louisiana and Hanford, Washington, simultaneously recorded a signal lasting approximately 0.2 of a second, the stretching and compressing of spacetime produced by 2 black holes, each approximately 30 solar masses, spiraling into each other 1.3 billion years ago. The signal matched the predictions of general relativity so precisely that the match itself was a confirmation of the theory to a new level of precision. LIGO had been under development since the 1980s. The path from concept to detection required decades of instrumental development, the construction of facilities capable of measuring displacements smaller than 1,000th the diameter of a proton, and the sustained funding and institutional commitment that those decades required. Gravitational wave astronomy matters to the story of the dying because gravitational waves are one of the few probes available to the very early universe to the conditions that set the initial entropy, that produced the improbably ordered beginning that Penrose put a number on. Inflation, if it occurred, produced a background of gravitational waves, a stochastic hum of spacetime perturbations that permeates the universe and carries information about the energy scale and dynamics of the inflationary period. Detecting the primordial gravitational wave background would be, in a sense, the closest anyone has come to directly measuring the origin of the dying, to reading the conditions of the initial gift of order that the entire subsequent history of the universe has been spending. The signal is extremely faint. Detecting it requires space-based gravitational wave observatories, instruments like the Laser Interferometer Space Antenna, LISA, which is designed to detect gravitational waves at much lower frequencies than LIGO, produced by different sources on different timescales. LISA is in development. The science it would enable includes the measurement of mergers between supermassive black holes, the kind of events that will define the black hole era of the far future, and potentially the detection of signals from the very early universe itself. If the primordial gravitational wave background is detected, the amplitude of the signal constrains the energy scale of inflation. From that constraint, you can calculate the specific conditions of the inflationary period, how fast it proceeded, how long it lasted, what the inflaton field was doing. Those conditions bear directly on the initial entropy state that Penrose calculated. The measurement would not tell you why the universe began ordered, but it would tell you more precisely how ordered it was, which tightens the constraint on the probability Penrose estimated. The probability may be higher than his calculation suggests. If inflation produced a lower bound on the initial entropy, it may be lower. The number on Boltzmann's tombstone, applied to the actual initial conditions, would be revised. This is what the current edge of cosmology looks like. Not the clean arc from discovery to implication to endpoint that most treatments impose, but a series of open questions, each of which bears on the others. Each of which is being worked by specific people at specific institutions with specific instruments. Each of which could resolve in a way that changes the character of what was thought to be known. The Hubble tension may be systematic error or new physics. The initial entropy may be constrained by gravitational wave observations that have not yet been made. The proton lifetime has a lower bound set by experiments that have been running for decades and have not yet found what they are looking for. The mechanism of Hawking radiation's information preservation is accepted as a conclusion without an established mechanism. The cosmological constant problem, the 120 orders of magnitude discrepancy, has no accepted solution and has not moved substantially toward one in a quarter-century of serious effort. These are not gaps at the edge of a nearly complete picture. They are gaps at the center of it. The accelerating expansion is measured. Everything about why it is accelerating, whether the acceleration is changing, what the acceleration implies for the ultimate fate of everything, these are open. The dying is confirmed. The mechanism of the dying is not understood. The timeline of the dying depends on measurements not yet made and questions not yet resolved. Perlmutter, in interviews given after the Nobel Prize, has described the discovery of the accelerating expansion not as an answer, but as a question that arrived wearing the clothes of an answer. The data gave you a number. The number gave you a conclusion. The conclusion gave you a framework, dark energy, the cosmological constant, the standard cosmological model with its specific parameter values. And the framework, when you pushed on it, gave you the cosmological constant problem, the Hubble tension, the Boltzmann brain problem, the question of what dark energy actually is and why it has the value it has. Each answer produced a deeper question, and the deeper questions are harder than the shallower ones they replaced. This is not unusual in physics. It is the structure of the enterprise. But in this particular case, the deeper questions are not merely technical. They bear on whether the model that describes the universe's death is correct, whether the heat death is actually the endpoint, whether the timescales derived from the current model are right, whether dark energy is constant or evolving, whether the universe's future is the quiet, asymptotic approach to minimum temperature or the violent structural dissolution of the Big Rip. The open questions are not details. They are the shape of the ending itself. In the absence of resolved answers, cosmologists work with what the data gives. The data gives an accelerating expansion. It gives a cosmological constant consistent with the measured value within current error bars. It gives a universe whose age, composition, and expansion history are specified by the parameters of the standard model to a precision that was unimaginable 30 years ago. From those parameters, the future can be calculated not with certainty, because the open questions are real, but with enough precision to describe the sequence of events that constitutes the dying. The description is honest about its own uncertainty. This is rarer than it sounds. The heat death is derived from a model that has known gaps. The Big Rip is a possibility that current data cannot exclude. The Boltzmann brain problem is a logical consequence of the model that the model has not resolved. The information paradox is acknowledged as unresolved by the people who study it most carefully. Cosmology, at its current frontier, is a field that knows more about the universe than any previous generation, and is more aware of what it does not know than any previous generation, and these two things are not in tension. They are the same thing. The more precisely you measure, the more precisely you can specify what the measurement does not reach. Vera Rubin understood this. She said in interviews, more than once, that she expected future measurements to produce surprises that the universe was not obligated to conform to the models built to describe it, and that the models were always provisional in a way that the language used to present them sometimes obscured. She said this as someone who had spent a career finding things the models did not predict. The flat rotation curves were not predicted. Dark matter was not in the cosmological model before the evidence required it. The history of cosmology is substantially a history of evidence arriving ahead of the frameworks built to absorb it, and the frameworks being revised, and the revision being credited to the people who built the new framework, rather than the people who found the evidence that made the old framework untenable. Dark energy is in the model now. The cosmological constant is in the model. The accelerating expansion has a name and a measured value and a Nobel Prize. What it does not have is an explanation. The model contains dark energy as a parameter without containing dark energy as an understood physical entity. The number is in the equation. The equation does not say what the number means. This is where the field has been for 25 years. It is where the field is now. The measurement that Perlmutter made in Building 50B, after 3 months of looking for his mistake, produced a revolution in cosmology that was real and immediate and consequential. It changed the standard model. It earned the Nobel. It is in every textbook written since 1998. And the revolution landed the field in a position from which the central question it raised has not been answered. The cosmological constant problem is as open as it was the day Ries ran the numbers. The Hubble tension has widened. The proton is still unobserved in decay. The primordial gravitational wave background has not been detected. The dying continues on its own schedule. There is something specific that happens to a person who spends long enough with this material, not as a thought experiment, not as a subject of intellectual interest, but as a thing that is actually true about the situation they are in. The universe is approximately 13.8 billion years old. The stelliferous era will last approximately 100 trillion years. The black hole era will last approximately 10 to the 90, 2 to 10 to the 100 years. The dark era will last, in any meaningful sense, forever. The fraction of the universe's productive history that has elapsed so far is approximately 1/10,000th. We are, by any cosmic accounting, at the very beginning of the dying. The middle territory is not thinning yet at any rate the current sky reflects. The stars burning tonight will burn for billions of years. New stars are forming now, from gas clouds that have not yet collapsed, in galaxies that are still in the active phase of their star formation histories. And yet the process is irreversible. The entropy that has already increased cannot decrease. The hydrogen that has already been converted to helium in stellar interiors cannot be unconverted. The galaxies that have already receded beyond the cosmic event horizon cannot return. The direction is fixed, has always been fixed, was fixed at the moment the universe began, in a state that could only become less ordered. The irreversibility is not a future condition. It is present now in every process occurring in every star, in every galaxy. The dying is happening at the rate the dying happens, and it has been happening since before the sun ignited, since before the Milky Way assembled, since before the first star lit in the early universe out of the hydrogen and helium the Big Bang produced. What changes is only what you do with that. Not what the universe does with it. The universe does nothing with it, because doing requires an agent. And the universe is a process, rather than an agent. But the temporary configurations of matter that the process has assembled, in the middle territory, the ones capable of measuring supernovae and building spectrographs, and spending 20 years defending atoms, and dying 2 years before the confirmation arrives, these configurations do something with it. They measure it. They name it. They calculate the timescales. They sit at 28 years old with the number that comes back wrong and feel dread before they feel triumph. Because the dread is the more accurate response, and some part of the brain that runs the calculation before the brain can articulate it knows that. The dread is appropriate. It is the appropriate human response to a finding that is true in every direction you extend it backward to the improbably ordered beginning, forward to the asymptotic approach to minimum temperature, Inward to the cosmological constant problem that has no solution. Outward to the cosmic event horizon that is already sealing regions of the universe away from each other permanently. The finding is not comfortable. It was never going to be comfortable. Perlmutter did not spend 3 months looking for his mistake because he expected to be comfortable with what he found if the mistake was not there. He spent 3 months looking for his mistake because the alternative required him to tell the world that the universe is accelerating toward an end driven by something with a name and no explanation, and that the process started long before anyone was here to notice it. He could not find the mistake. That is where the measurement lives, not in the Nobel citation, not in the textbook summary, not in the clean narrative of discovery and implication and endpoint. It lives in the 3 months of assuming fault, in the systematic checking of dust and calibration and selection effects. In the moment, each check came back clean, and the number remained. It lives in Rios at 28, calling the data albino, and running it again. It lives in Zwicky calling his colleagues spherical bastards, because the evidence was real, and they would not look at it. It lives in Boltzmann defending atoms for 20 years, and not surviving to see the defense vindicated. It lives in Rubin measuring galaxy after galaxy, flat curve after flat curve, building the observational foundation for a model of the universe that would be used to discover something she was not credited for discovering. The dying started before Earth existed. It started at the first second, in the dissolving of an initial order so improbable that the probability requires a number larger than the count of all particles everywhere. It has been proceeding through the burning of every star that has ever burned, and the death of every star that has ever died, and the scattering of every element that has ever been scattered, and the coalescence of every planet that has ever formed, and the emergence of every chemistry that has ever assembled itself from stellar ash, in the thin habitable band of some ordinary star, in some ordinary galaxy, in the middle region of the entropy spectrum where complexity is briefly possible. It is proceeding now, at the rate set by the cosmological constant that nobody can explain. In a universe that is the most accurately measured and least understood it has ever been. The measurement will continue. The instruments will improve. The Hubble tension will resolve or it will not. LISA will fly or it will not. The primordial gravitational wave background will be detected or it will not. The proton will decay or it will not. And the Super Kamiokande tank in Japan will keep watching the ultra-pure water for the signal that has not yet come. Year after year, the photomultiplier tube sensitive to a single particle's light. The scientists on shift doing what scientists on shift do, checking the system, logging the null results, updating the lower bound on the proton lifetime, moving the constraint another increment in the direction of stability without ever reaching it. And the entropy increases. On the schedule it has always kept. Toward the endpoint it has always been approaching. Driven by the initial gift of order that was given at the beginning for reasons physics does not yet know, and that physics has been spending itself trying to understand ever since. At the cost of careers and decades and recognitions that arrive too late or not at all, producing knowledge that is more precise and more uncertain than it has ever been simultaneously, in the brief window of the middle territory where the complexity required to ask the question is possible. The window is long by human standards. It is a transit zone by any other. The number Saul Perlmutter kept getting back was not his fault. It was the universe, doing what it has always been doing, finally producing a measurement legible to the matter assembled inside it, matter that was in stars before it was in the people holding the instruments, matter that will be scattered and cooled and separated for timescales that make the entire history of the question irrelevant. Matter that organized itself briefly in the middle territory into configurations capable of dread, and used the dread honestly, and found the thing nobody had said plainly, and said it. The universe is dying. It has always been dying. The process that started before Earth existed is the process that produced Earth, and everything on it. And everyone who has ever looked up and wondered what was out there, and then built the instruments to find out. The dying is not the opposite of the living. It is the condition the living occurs inside. The stars do not burn despite the entropy. They burn because of it, because the initial gift of order created a gradient, and the gradient drives every process that has ever occurred, and some of those processes, in the middle territory, are complex enough to notice. This is the most honest version of the title's promise. The universe is dying for a reason. The reason is that it began. The process started before Earth existed, because the process started at the beginning of everything, and Earth is a recent development in a very old story. And the people who found this out, who built the instruments and ran the numbers, and sat with the dread, and defended the findings, and died 2 years before the confirmation and were passed over for the prize, are the middle territory's way of knowing itself. Briefly, accurately at cost. The entropy increase continues. The window stays open a little longer. The watching continues while it does.